This is a lecture over the intermediate value theorem and the bisector method for finding roots of continuous functions for Math 107, Chapter 3. The intermediate value theorem says for continuous functions says something that will seem intuitively obvious. Let's say we know that the function takes on the value 4. That's value 4 here, okay. And that, I could draw a line. So it takes on the value 4. And I know that it takes on the value 6. And it's a continuous function, like a polynomial. That's why we're bringing this theorem up. Well, the intermediate value theorem says that if the function takes on two values, say 6 and 4, then it takes on, or part of its range, you can think of it that way, is all the numbers between 6 and 4. Now, if it didn't take on some of them, of course there would be a gap or a discontinuity there, in which case it wouldn't be a continuous function. So like I said, this sounds intuitively obvious, but here's how we use it. Let's say this is the polynomial that we're dealing with, and this is its graph. Now if I can find two values of x where the function takes on a negative value, for example right here the function is negative. Right? I kind of missed it, but you get the idea. And then I find another value where the function's positive. So here's a value of the function that's positive. Here is a value of the function that's negative. The intermediate value theorem says it takes on all the values between this positive number and the negative number, and so that would mean it would take on the value 0. So in practical terms, this means if I can find a value of x where the function's negative and a value of x where the function's positive, I know somewhere between those two values of x lies a root, because the function has to cross the x-axis, and that's what I'm looking for. So here's the root right here. In other words, we have bracketed the root, or you might say we've trapped the root between these two values of x. Remember, a root is a value of x for which the polynomial is 0. For this particular function, I should tell you what it is. It's p of x is x squared minus 2. Then I have found here two values of x. One, x equal 1, and when x is 1, this polynomial is 1 squared minus 2. It's negative 1, so it's less than 0. At another value of x, I keep hitting that button, sorry, x equals 2, the polynomial is 2 squared minus 2, so that's going to be 4 minus 2, so it's a positive 2. In this case, it's greater than 0. And those points are right here and right here. Okay. So I have found two values of x. I'll call this one x with a negative sign with it, because at this value of x, x equal to 1, the polynomial is negative. And then I have another value of x, in this case x equals 2, and I'll call it x with a little plus sign or a p as subscript to denote that that value of x, the polynomial, is positive. So somewhere between 1 and 2 there is a root. And if you had the graph, of course, you could get annoyed. If you had the graph, you could just see it. But if you don't have the graph in your computer and all you have is numbers to work with, you can find the root. So here's the idea. We have bracketed the root between x equal 1 and x equal 2. So now, to use the bisector method, we do what are called iterations. An iteration is like you have a stylized set of procedures, and you're going to repeat that set over and over. Every time you repeat it, it's called an iteration. So here's my iteration. This is what I will be doing. I want to find another value of x that's closer. What I want to do is take this bracketed region and I want to make it smaller and smaller and smaller and smaller, keeping the root always in the middle of the bracketed region. In other words, I want to move this one down and this one up in such a way that I finally am very close to the root. So I have to do that in a series of steps or iterations. So here's what I do. I calculate a new value of x, and I do that by averaging the two values that I have. This was my -1 and this is my positive. In this case, I would average the two x's. Now some people try to average the y's, and that's something that you do in a different method, not this one. Here you average the x's. So you take 1 and 2, add them together, divide by 2, and I get 1.5. Okay. Now here's the 1.5 right here, approximately. Now I don't know whether this 1.5 is a result of bringing this down or this up, so the way I figure that out is I put the 1.5 back into the polynomial and I find out if it's positive or negative. So I put 1.5 into the polynomial, which means I'll have 1.5 squared minus 2. This ends up being greater than 0. And you can see it from the graph, it's greater than 0. So that means I can forget all about this, and now my trap or bracket consists of that region. And that was one iteration. And now I repeat the process, but I'm going to use 1 and 1.5 for the next iteration. So I have to erase some of this. Okay, so I find a new value again, and I take the 1 and the 1.5. I divide them by 2, of course get 1.25, which is about here. Now I don't know whether that was a result of bringing this bracket up or that one down, so I find that out by putting the 1.25 into the equation and find out if it's negative or positive. So when I put it in the equation, of course I find this value, I find that it's negative. So now I can get rid of this, and now my bracket consists of here to here. And that was the second iteration. And now I take those two numbers and I add them again. Let me erase some of that. So my new value, I'm going to take the 1.25, because that was my that was this value right here, and the 1.5, the one that's on the other side of this bracket. I divide by 2, okay, and I get 1.375. I don't know where that is, so I put that into the equation, and if you put that in the equation, you find out that it's negative. So that means your 1.375, which is right here, has to do with this point. So you see we're kind of closing in on the root, and that's the bisector method. Now you could say, well, am I ever going to really hit the root? The answer is probably not, but you're going to get close enough. And there's two ways to stop. One, you can write this into the computer easily, and then you could tell the computer to do so many steps, like 10,000. You say after 10,000 iterations, stop. Right? That's one way to do it. Just say that's whatever you come up with is good enough. Take the last value of x and call that the root. And the other way is to look at, as you know, a word in a computer is only so long. So there's a certain precision that the computer has, and you decide what is, of course you can't go over that precision. You can't get more precise than that. You're just fooling yourself if you think you do. But on the other hand, maybe only so much precision is needed for your particular problem. So if you find out that polynomial of x, its absolute value is, say, less than 0.0001, you could say that's close enough to 0 and I'll stop. So when you get to this stage, instead of just trying to find out if it's positive or negative, you also check its value, and if it's close enough to 0, then you stop. So this is the bisector method. It will find the roots. They can be positive, negative, rational, or irrational. It will find them. It works very well, and it gets very close to the roots, and it doesn't take that long. So I want to go over the steps again. So for the bisector method, you have some polynomial in x, and you find two starting values, and sometimes you have to just guess those two values and try them out. But you have to find one value of x where the function's positive, and then you have to find another value of x where the function's negative. For example, I could have used 0.5 because the function's negative here. We could have used 3 because the function's positive here. And those are your starting points. You need two of them. The intermediate value theorem tells you that there's a root somewhere between 0.5 and 3 because the function has to go from negative value to positive value, and it has to do it continuously, so therefore it has to somewhere in there take on the value 0, which is the one we're seeking right here. So you can think of this as some kind of bracketing or trapping of the root. Right, now you want to find out, you want to, of course, cinch this bracket down. So to do that, you keep finding different values of x. Remember, you average your x's. So you do that by taking the plus 1 and the negative 1. In this case, it would be 0.5 and 3. And you divide by 2. And that's supposed to be adding because you're averaging them. So when I divide, I get some number in here, right in the middle. Now I don't know what effect this has on this bracket, on this trap, until I try it out. So I would take this new value and I'd put it in my polynomial and I'd find out what it is. We have the graph, so we can tell right here it's going to be positive. When it's positive, you look at your old positive number and you can just disregard it, because now you have a smaller region to work with and you only work with from here to here. Then again, you take the average between this number and the 0.5, which is 1.75, right? And you average that and you come up with another x. So you test it out, and you would test this out in the polynomial. You would find out that it's negative, so you disregard this old one, and now you see you've got a smaller interval. You've kind of trapped the root, and you sort of cinch down on the root, and then after so many iterations or so much accuracy, you stop. So that's the bisector method for finding roots of polynomials.